Okay, welcome. It's our last press conference of the day, our Geoscience Grab Bag number 2. We have 3 wonderful presentations today, all tied together by the fact that we thought they were really fun. So first we're going to have Anna Voigtländer from the Helmholtz Center in Potsdam. She's going to talk about how tall mountains can be. And then we have Anna Riddell from the University of Tasmania, who's going to talk about earthquakes, and Chris Goldfinger from Oregon State University, who is also going to talk about earthquakes. I'm going to turn it over to Anna.
Thanks. So actually, I'm just going to talk to you about something that is where we came up with 3 ways how we explain how tall mountains can actually be. And so it's not only about how tall mountains can be, but also how rocky, steep mountain cliffs and faces can actually persist, which we find all over the world and probably also beyond Earth. And so one reason why we've been looking into this is that we don't really have any good explanation why we have steep cliffs. Like, for example, this is El Capitan, our half dome, and we can't really explain when something maybe falls off and why they persist and have this height. So in general, people have been explaining these with different modes of failure. So usually what we do is we explain it by 2 modes. Either you can think about it as you compress something until you crush it. So the height kind of is the load you put on it, and at some point it will just crumble and crack. Or actually what most people have been using so far is to explain it is you compress it and at some point you shear it off. And if you look into rock mechanics, which is steep rock cliffs are actually made of, there's a third mode in which things can break. And that's when you compress something, actually what you do, you create a tension to the sides, to the free surface. And you can create, parallel to the surface, to the free surface, you can create cracks. So, and another thing from rock mechanics is quite interesting. So I wanted to bring you chocolate, but I couldn't find any suitable chocolates. But imagine you have a piece of chocolate and you squeeze it. How much load do you need to apply, actually, to deform it? And at what load will you induce tensile failure, shear failure, or compressive failure? So if you imagine you squeeze a piece of chocolate, you probably break it like this. So first of all, with 40 to 60% of the maximum load you can apply, you will get tensile failure. With fixed 50 to 90%, you get shear failure. And if you squeeze really, really hard, you'll crush it, and then you can eat it. So, and that's the same for most hard rocks we have. But very funny, we don't really have any failure limit criteria, so a way how we could describe why things break, at what limit, for any tensile failure. So there's the existing ones are a crushing strength limit, a shear strength limit, and also a limit to topography. But we don't really have something which is a tensile strength limit, which we use to describe the height of mountains. So I've always been talking about the height of mountains or the load, and what we actually mean by that is that we have the relief and we have the slope, and those together with the density of the rock and the gravity as the acceleration, make up the load we have. So what we can do is we can actually assume we have a certain rock type, and we can predict with these assumptions how high actually some mountains can be or how steep they can actually be. So we did this for some rock types, and we compare them to some very famous rock walls you find on Earth. And as you can see, we've took very common rock types, so granite, gneiss, limestone, and the sandstones, and we plotted the mechanical failure limits you would expect and the height and the slopes you could get from these rocks. And then we compare it, for example, to Half Dome and El Capitan, or in the Gneiss to some very famous mountain slopes in Europe, like the Matterhorn, or the Hochwanner. And you can see that most of our steep slopes plot below the failure limit we would predict. And that's because we just used some intact rock properties. But you can see that all the other failure limits, for example, for crushing or for shear strength, they are way beyond our limits we can observe in nature. So this is just a first idea, and we are still collecting more data on steep rock cliffs, and we hope to stimulate some discussions on how we can use this more, because we can maybe not only explain slope failures, like we had a few years ago on Half Dome, but maybe also explain landscape evolution. So the implication of our work, we think, is that we do see that the tensile strength limit is in good agreement with the height of steep, hard slopes, rocky slopes. We don't propose it in contrary to the other criteria, but in addition, because it really fits this type of material. But another thing which we found when we set this up is actually we can also get some information on the failure dynamics we can expect. As I told you before, we find when we start crushing something at 40 to 60% of the strength, we can find failure which is parallel to the surface. And this is something we also observe in nature. So we observe a lot of times on steep cliffs that we get some spalling and rock falls just at the face, and which is propagating upwards. So we think this is also has some potential to also anticipate further hazards or rockfall damage. And if you have further questions, you can contact me via email or my co-authors. Thanks.
Good afternoon. There's been quite a long-held assumption that the Australian plate is tectonically stable and seismically inert. And so what that means is that we don't have a lot of earthquakes in Australia, or so we thought. Each of these grey dots represents an earthquake that's happened in Australia or in the Australian region over the last 12 months. And so we can see that there's quite a lot of chatter around the plate boundary, as we would expect, but there's also quite a lot of chatter in southwestern Australia, central South Australia, and also in southeast Australia, where we see some odd movements of the surface of Australia. Now, there's been a bit of a conflict. Some of our models and our theory suggest that the Australian continent should be uplifting, but a lot of our data in terms of tracking positions and how the surface of the Earth is changing suggests that the Australian continent is sinking. And so how do we look at this? What do we measure? Each of these blue squares represents a location where we're recording a position every 30 seconds. And that data at these sites has been going for almost 20 years, and so we can look at the change over time. Now, in terms of that odd seismic chatter across the Australian continent, we can look at that in terms of earthquakes on the plate boundary and how that might be changing the surface as we see it today. Now, we know quite well what the horizontal motion of the Australian plate is. It's about 7 centimetres a year, which is about the size of a tennis ball every year. It's shifting towards the northeast. But vertically, it's a little bit uncertain. Are we going up or are we actually going down? And that speaks to the conflict that we see between the models and theory and also the data that we're collecting and seeing. And so what my research was looking at, it's looking at the large plate boundary earthquakes, and if we can see that as a deformation signal or a change on the surface of the Earth at sites on continental Australia. And so looking at one earthquake that occurred at the end of 2004 down on the Macquarie Ridge just south of New Zealand, we see that a site in Hobart in Tasmania, looking at a change over time in the up coordinate, so this is a position time series. The series has been detrended in the time before the earthquake happened, and at the time of the earthquake, which is the red dashed line, you can see a change in the rate of subsidence at that site in Hobart. So what this is saying is that at the time of the earthquake and following the earthquake, we see an increased rate of subsidence in Hobart. Now, if we were to stick with the assumption that the Australian plate is seismically stable or tectonically stable, then we would expect to see the same rate of change at each of the sites across Australia. So let's take a look at another site. This site is up near Canberra, which is where my office is at the moment. But what we see is that not only is there an increased rate of subsidence, that rate is larger than the rate in Hobart. So we're already cracking the assumption that the rate of change at all of these sites should be the same. If we move a little bit further, we see that at Tidbinbilla, which is also near Canberra, we see a similar rate of change. And so what this change or the deformation across these sites is suggesting is that not only are we not stable, but we can also see why we're seeing a bit of a difference in what our models and our theory are suggesting as to what we see in our observations. Now, this has clear implications. You might have heard me saying that it's at the rate of a couple of millimetres per year and thinking, well, that's really small. But it does make a difference if we're looking at other rates of change across the globe, like sea level. And if you're measuring sea level with a traditional technique like a tide gauge, then you need to understand that that's a relative measurement from the tide gauge that's measuring sea level relative to the land that the tide gauge is attached to. And what we see in certain situations is that there's a rising sea level but also a sinking of the land. You get an increased sea level change in that area. And so we use a technique that's called global positioning, or GPS, to measure the rate of change in the land. And we can also link that to satellite measurements of sea level. And so we can create a loop where we're checking our measurements. And so a millimetre does matter. We're talking about measurements at the rate of a few millimetres per year, which are important for applications or measurements such as sea level change, also glacier and ice sheet change. We can also start to use these measurements of change over time to be able to look at hazard mitigation and also risk minimisation in regards to flooding, inundation, volcano eruptions and also landslides. And as we move into the era of autonomous cars, we need to have a spatial reference system that allows us to align spatial data. And we can't do that if the land underneath us is moving. In Australia, we have a lot of precision agriculture, and so this particularly links to knowing where the tractor is and also where your farm boundaries are so that you don't get a rogue tractor happening. So the system that I'm using to make these measurements is global navigation satellite data. And you've got the American system here, which is GPS, but there are also a couple of other global satellite systems that provide this data. And we use very high quality electronics for receiving the signal from the satellite. And it gets quite weak after travelling almost 22,000 kilometres down to the surface of the Earth. And so these are the types of instruments and the types of setups that we have installed all over Australia. So each of these dots represents where we have a permanently operating site that is collecting data every 30 seconds, and we can track that change over time. And so what I would like to wrap up is tide gauge measurements require a correction for vertical land motion if you're wanting to get an unbiased record of sea level change. Horizontal motion of the Australian plate is quite well known, but we're still a little bit unknown in terms of what the vertical motion of the Australian plate is doing. And we can also see that there's a deformation or a change over time that we can see from large plate boundary earthquakes down to the southeast of Australia, but also up in the northwest as we see the Sumatra, Andaman, Banda Trench earthquakes as well. So thank you very much for your time. I will pass it over to our next presenter.
Well, good afternoon. I apologize for committing the geologist's sin of keeping us all from the free beer just outside, so I won't keep you too long. My email is up here, and this is a long-term project sponsored by USGS and NSF as it relates to both the Cascadia subduction zone and the San Andreas Fault. And so what I specialize in is submarine paleoseismology, and basically earthquakes trigger submarine landslides that roll down into deep water and leave deposits here, which we can core from a big ship with a piston coring device like this. So we basically lawn dart the stratigraphy and collect a series of deposits, which are sometimes earthquake deposits. And so this helps us get to generate long earthquake records in a variety of places around the world. But this is relatively new science, and we're still learning lots of things. So we're going to leap into Cascadia now, and this is the southern part of the Cascadia's subduction zone, and you're seeing it from the west with the water drained out. So this is Cape Mendocino. This would be about Eureka, California, Crescent City, California. San Francisco is off the page to the right. And what this is a triple junction where the San Andreas Fault here in red meets Cascadia, the plate boundary also in red here, and a third fault called the Mendocino Fault would be right here. And so this is kind of a special place where two great faults come very close to each other. And these are the core samples that were used. We're going to focus on mostly the best of the best, the ones at Trinidad Canyon here on the Cascadia side, and Noyo Canyon on the northern San Andreas Fault side. And so you'd expect that these canyons would faithfully record Cascadia earthquakes. This one would faithfully record San Andreas earthquakes. But what I'm going to show you is that both canyons actually record both fault systems. And the range is about 110 kilometers either way. And so that's key to the story. And so in Cascadia, this is the most recently published version. This is a compilation of both land and marine paleoseismic sites, that is subsided marshes along the coast and tsunami deposits, as well as marine turbidites offshore. And so this data incorporates both of those. And we're going to look down here in the deep south of Cascadia where this question mark is and try to sort out this complex area where we have multiple fault sources for the turbidity currents. And so I'm going to flip-flop back and forth between the Cascadia side and the San Andreas side. So let's start in Cascadia. And this is the upper few hundred years of one of the better cores on the Cascadia side. And we have at the base of this section what we call T1. This is the 1700 Cascadia earthquake, January 26, 1700, about 9 p.m., based on Japanese tsunami records. But it's not the most recent event that's affected this core. You can see there's several more on top. And so up at the top, we have what we believe to be the 1992 Petrolia earthquake, a 7.1. We can date this pretty precisely using bomb carbon, which is nuclear waste products refinement to radiocarbon that gives very precise ages. The next one down is the 1906 earthquake. And so we've modeled this age very closely to that time, and so this is key also. So we have historic events in these cores, and in paleoseismology, being able to pinpoint a historic event is a key important detail. Plus, we're clearly recording San Andreas earthquakes on the Cascadia side of the system. So that's also very important. And then the 1700 earthquake down below. So here's the age of the radiocarbon modeled age of the 1992 earthquake. Here's the 2 sigma range here with a median of 1992 plus or minus a bit. So having these historical events is really important, and it's also important to note that we can record reliably events down to magnitude 7. Our previous floor we thought was about 8. Now we know that we're recording magnitude 7 earthquakes. So now we're going to jump back to the San Andreas side of the system. Here we're in Noyo Canyon, 110 kilometers south of Cascadia, and this is an event here that I'll describe in a little detail. So it's got a relatively fine-grained base. This is a CT scan with this, and the bright light yellows and whites are sand, and all the rest of this stuff, the yellows are silt, and the rest of this is mud in between the earthquakes. And so what we have here is, this is also at the time of 1700. So it turns out the San Andreas Fault also had a 1700-ish earthquake that ran all the way to San Francisco. And so when we look in this core, what we'd expect to find is the San Andreas 1700 earthquake and the Cascadia 1700 earthquake. But instead of 2 deposits, we find just 1. And for 130 years in this direction, younger, and 500 years older, there's nothing else there. So where there should be 2 deposits, there's just 1, and we find this complex deposit with a fine-grained part at the bottom and the coarse-grained sandy part at the top, and a boundary between the 2. So this actually looks like 1 deposit, but it's actually 2 deposits, one on top of the other. And it's also strange because the coarse-grained deposit, part of the deposit, is at the top. Well, these turbidites always have the coarse grained part at the bottom. That's just as if you had a Coke bottle full of sand and you shook it up, all the sand would go to the bottom. And so this turbidite is basically upside down, a double-decker turbidite that's upside down. And it's not the only one. There are 7 others, in the last 3,000 years that are also upside down and have this complex, coarse part at the top and fine part at the bottom. So here's just another view of that same deposit from 2 different cores, with a fine part at the bottom, a coarse part at the top. And again, where we look in that time range where there should be 2 1700 earthquakes, we only find 1. And so we now think that this bottom part is the Cascadia 1700 earthquake, and the top part is the San Andreas 1700 earthquake. And it's coarser at the top because the San Andreas fault is right next to this site. It actually cuts this canyon system, so we'd expect it to put a lot of sand down during one of its earthquakes. And so this is a rogues gallery of all the other 7, multiple examples of the other 7 deposits that look this way. And so you see again and again the coarse part at the top, the fine part at the bottom, over and over and over again in each one of these. So there are 8 of them total in 3,000 years. And before that time, these records go back 10,000 years. We only have 2 examples, one at 4,200 and one at 8,400, that are that way. All the rest of them look like this one. And this is the turbidite from the 1906 earthquake. So this is what a San Andreas only turbidite looks like, fairly thin and simple, compared to the ones that match up in time with Cascadia. And each one of these has a radiocarbon counterpart that matches in time, plus or minus quite a bit, because radiocarbon won't allow you to match things very closely. It's more like plus or minus 100 years. And so if these temporal counterparts really are Cascadia and San Andreas together, how much time could have elapsed between the deposit of the top part that we think is San Andreas and the bottom part that we think is Cascadia? Well, what we would look for is this dark blue material. This is the material that's deposited between earthquakes. We would look for a band of this dark blue material somewhere in here. Remember, the sand is orange and yellow. The light blue is silt, and the dark blue is the stuff deposited between earthquakes. And we basically don't see any of that here or in any of the rogues gallery. So we see this repetition of very close stacking of these events. We've got 7 cores on each fault system and 8 of these events. So that's 56 replicates that we have, and we don't see passage of time in that obvious sort of way. The age models suggest that if we were missing about 30 years or more in time due to erosion between the 2 events or something, that we would see that. That would be visible as a kink in the sedimentation rate curve. And so in one well-known example, we know that we can resolve differences of 22 years, and we know we can resolve a difference of 12 years in one case. So we think what's missing, if there's anything missing at all, couldn't be a lot more than that, or we would see it. So this suggests the difference between these things in time, which we can't resolve with radiocarbon, is probably less than 2 decades at least. And so I'll just show you one more example. This is Cascadia Event T4. This is a well-known event dated on land and offshore as well. This is it here. This is also part of it going off the top. So the lower unit is very similar to what we correlate and see as Cascadia T4 for 1,000 kilometers to the north, all the way to Canada. The upper unit, though, this upper unit only appears when you're close to the San Andreas. Doesn't appear anywhere else. And so here's another core, 18 kilometers to the north. By the time you get here, this upper unit is gone. And this is how T4 in Cascadia, the 1,200-year-old earthquake, looks for hundreds of kilometers to the north. And so this example suggests that possibly the timing between these 2 things could have been much closer than a couple of decades. It looks like this part, if it is the San Andreas, was deposited during the deposition of the bed triggered by the Cascadia earthquake. And so in summary, we have segmented Cascadia earthquakes that are well known from the land and the marine paleoseismic record. And we're now able to image smaller earthquakes down to 7.1 in the southernmost part of Cascadia. We're also able to image San Andreas earthquakes that are clearly on the Cascadia side of the triple junction, which is right here. And we're clearly able to image southern Cascadia earthquakes on the San Andreas side. So we're seeing both faults triggering turbidity currents on both sides of the triple junction. And so what we think now is that the very close stacking events in both systems may represent evidence of stress triggering of one fault by the other. And the series of 8 of them in 3,000 years may represent partial synchronization of the two fault systems over that time. Before that time, it didn't exist, and it may have ended with 1906. So that's it. Thank you.
Well, this is when we open the floor to questions from reporters in the audience. Sparse but valiant crowd here. Would anyone like to ask a question? Yeah. Do we have anyone on the chat, Sarah? Okay, we'll give them a minute. Any questions from anyone in the audience? Okay.
I was curious about the temporal, this coupling of these events has a beginning and it's maybe an end in 1906. That's not clear. Do you have any hypotheses about why that would be? In other words, what would couple them and then what would uncouple them?
Yeah, that's a really good question. Is this working okay?
Yes.
Okay. A well-known earthquake mechanics guy named Chris Schultz wrote a paper in 2010 where he proposed the idea of fault synchronization. And it's basically that if you have an earthquake on one fault system, we now know that it will transfer stress to the surrounding area, and it'll unstress some areas, and it'll increase stress in other areas. And so this system is not particularly favorable to transferring stress from one fault to the other, but it does do it just poorly. And so what I think may be happening is that the two faults have repeat intervals that are very similar, 220 years on the San Andreas side on average, and about 240 on the Cascadia side. So it seems to me almost inevitable that they'll sync up for periods of time and then drift out of phase after that time. And it's not unlike, tail light or blinker lights on cars that sync up for a while, only in this case, they're actually interacting. So when you transfer stress to another fault, you actually, if you increase its stress, you may cause it to rupture a little bit earlier than it would have. If you decrease its stress, you may retard its next rupture. And in this case, it may be clock advancing, essentially, the San Andreas fault, so that they sync up for a little while, but their natural rates are different, a bit different, so they would drift out of phase. Great
Do we have
question.
any other questions in the room? We have a question on the chat. Oh, great. Question from the chat.
So for Chris Goldfinger, Rick Lovett is a freelancer, and he asks, what would cause the synchronization as opposed to simple triggering, and why would the synchronization quit?
Very similar question, but basically the reason is the fault's natural periodicity, if they were separated, are a little bit different. So when you trigger one earthquake, we're used to seeing now, for the last 30 years or so, we're used to seeing one fault stress triggered by another fault, and we think of that as a one-time thing. But over time, if you think of two faults going off at repeat times that are similar, they could sync up and interact for periods of time that could be much longer than one event, in this case, around 3,000 years. And so the groundwork for that theory is out there in Chris Schultz's paper, and it's been repeated in several subsequent ones. But just drifting out of phase would explain the end of it. But we also don't know that 1906 was the end of it. 1906 wasn't synced up, obviously, but there were others in that 3,000 years several others that were also not synced up.
Any other questions? Looks like, oh, we have one more in the back.
I'm Madeline Nash, freelance. I forgot to
Oh.
add that before.
Thank you.
Is there, this is sort of a two-part question, is there a directional bias? In other words, is the San Andreas during this time period more likely to trigger Cascadia or vice versa, or is it 50-50? And also, is the geometry of the triple junction an important factor in linking the two faults?
No, also great questions. So it looks like, and I'll try to show this in a little more detail on Friday at my talk, but it looks like a strong bias toward Cascadia triggering the San Andreas, simply because of the stratigraphic data. But theoretically, the Cascadia subduction zone should have quite a bit more energy release than even the largest San Andreas earthquake. So having San Andreas trigger Cascadia would be a bit of the tail wagging the dog. Not that you couldn't do it, but it's not energetically very favorable. And then, I'm sorry, what was the second part of your?
Does the geometry of the triple
Oh, yeah,
junction
yeah.
have a role to play here?
Yeah, it certainly does. So the geometry for the stress transfer in either direction is not favorable at all. It's actually very poor. And so we wrote a paper in 2008 that talked about this in terms of the radiocarbon overlap, but we didn't have the stratigraphic evidence. And Roland Bergman at UC Berkeley did the modeling, and it really wasn't favorable for this at all. It lit up and increased stress on very small parts of the northern San Andreas and decreased it on others. So it's not a poster child for, this is an ideal mechanism. And so you've got the vertical San Andreas and the dipping Cascadia subduction zone, and they just don't interact in a particularly nice way. But nevertheless, the stratigraphic evidence seems to support it. And what we did in the original paper and what Roland modeled was, if you also add the Mendocino fault, that third fault, into the rupture, if it participated in the Cascadia rupture, or if the Mad River fault or some of the other Humboldt County thrust faults participated, then it became much, much more favorable. And so we don't know if that has ever happened in real life. There are people that are working on that, and there's some talks at this meeting that address that. But if that were to happen, then it becomes a very favorable stress transfer mechanism.
Questions on the chat?
This question is for Anna Voigtländer, and it's also from Rick Lovett. What are the maximum theoretical sizes of the cliffs for the different types of rocks? It was hard to read the slide online.
Okay. So the maximum heights we have depending on the material we looked at, range between like 2,500 meters to about 1,500 in the sandstone. And that's about how high a lot of these cliffs are.
Thank you. Great. Do we have any more questions in the room or on the chat? All right. I'm going to close the session then. Thank you to our panelists, and we will resume tomorrow morning